Welcome to Chapter 3A. In this segment, we'll explore the peptide table, your central workspace for reviewing all processed peptide data. You'll learn how to navigate the table, filter results, and begin interpreting key metrics from your HDX experiment. Let's take a look.
Since we mentioned the peptide table on the bottom of the screen, let's cover some of the features that this view provides. So it will list all of your peptides in your project in order of ID, which is the same order that they come in from the peptide list. This is sortable by start-stop. It's actually sortable by most of the fields that you see here, by every single header. So you would have your ID, you would have an assessment. The assessment is the relative quality of that peptide throughout the project. A green assessment means that this peptide is good in basically every condition in this project. A yellow assessment means that there might be an issue with the peptide in one of the conditions. In this example, it's one of the time points. So what am I looking at when I say one of the time points? Well, each peptide will be measured in every protein state, which are listed horizontally here. So the first protein state, the control, the second protein state is the bound state, and under each state you have your time points in ascending order based on the time. So what that means is, okay, this peptide is red in the third time point in this protein state, is what this condition means. So that would be a yellow peptide, right? There are also red peptides that are not shown. The red peptides are considered not valid in any condition. So in order to see those, I just have to enable this filter, and I would have to scroll down, and eventually I would probably find a peptide that's not useful in some of the conditions. In this case, this peptide seems okay in MS1, but it just doesn't pass the filters that we set. So also, I guess it's missing MS2 data in the other replicates. So this is an example of a red peptide that wasn't used in any condition, and every single reason why this peptide was rejected is listed here as flags. For peptides that are accepted, or they're green or yellow, but still present flags, that just means that maybe one peptide measurement out of all of them has an issue. And in order to navigate to that issue, you would simply just click on the flag. When you click on the flag, the software will navigate to that exact peptide measurement, so that exact file for this peptide, where the issue is displayed here in the top table as well, which is broken down into each run in the set of replicates. So in this case, it's saying that the duration model that we're trying to fit to the data just doesn't fit quite well, and it's quite apparent from the MS1 data that this duration model isn't fitting the observed data very well. So we can't really trust it for its measurement, for its duration measurement. As well, it seems like in this scenario, the duration from MS2 is a little ambiguous. Some fragments are reporting high duration, some fragments are reporting low duration. So what happened is the software simply rejected this replicate for this peptide and has now been using the other two replicates to represent this peptide in this state. So 2 out of 3 replicates are still okay. We can still measure the stats for the peptide in that protein state. We need at least a minimum of 2 measurements to be able to calculate at least a very rough standard deviation for this condition. The peptide table, other than the fragment filter, it has a filter for the minimum number of fragments and the max %d standard deviation that it'll allow. So in order to show you that, I will just swap to one of the views here, which is a volcano plot, wood plot type of view. This is your comparative analysis type of views that you'd expect for HDX data. And in this scenario, what I will do is I will simply modify these 2 filters that appear on the global peptide table. So when I set the minimum number of fragments, what does that mean? The minimum number of fragments are the fragments that are measurable for the peptide. So for example, fragments that are not measurable can be used to identify a peptide, but cannot be used to measure its duration. Those fragments are not shown on this view here. However, those fragments are still stored in the background just to verify the peptide's identity. A measurable fragment is one that appears as red. So these, for example, would be used to measure the peptide duration. And so that is what this filter is doing. It's telling me what is the minimum number of fragments that I want a peptide to have to be able to measure its deuteration. So right now it's 3, so most peptides pass that condition. But let's see what happens if I increase that number to 5. So you can see here currently what I have is I have about 369 peptide measurements that pass both conditions that have at least 3 fragments. When I change that minimum fragment number to 5, then the number of peptides that pass that filter is now lower, right? So it is 296 peptides. And you can see that a lot of the noisy peptides have disappeared from the Woods plot. So this is just an easy way to control globally some of the filters. It's the same idea here with the max standard deviation. The standard deviation is just, it's exactly that. It's the standard deviation in a set of replicates. If your replicates have completely differing deuteration measurements, the standard deviation will be very high. And you can actually view that same standard deviation on this kinetics plot on the right, bottom right side. And so what I can do is I can decrease this filter. I say, okay, I can accept a standard deviation per state of 5%. Maybe I want it to be lower. Let's say I want a standard deviation, maximum standard deviation to be 3% for a replicate set. I can set it here. And as before, you see a lot of the outlier peptides have disappeared. And so this saves some of the manual work to click on peptides and delete them and so on. You can simply just modify these 2 filters. As long as your peptide coverage stays high, I would say that you should increase the number of minimum fragments and perhaps slightly decrease the maximum percent D standard deviation, although 5% is pretty reasonable.
That's a quick look at the peptide table and how to work with your HDX data at a glance. Next up in Chapter 3b, we'll dive into the peptide map, a powerful visualization tool to help you see uptake differences across your protein sequence. Let's keep going.